Okay, so let's go ahead and pick up where we left off. So over the last week, we've talked about a specific type of neural network model, the multi-layer perceptron. And so the goal of this model was to simulate a network of neurons as if they were akin to logic gates in a computer. So every one of these neurons had some effectively binary inputs and then produced binary output that was thresholded and so forth. So we experimented with them, we got them working, we got a feel for how they operate. But a lot of what I want you all to learn over the next project is that this isn't the only kind of neural network model imaginable. You know, there are actually very large numbers of different models, different families of neural networks that have different properties and, importantly, different biological inspirations. The brain's a complicated place, and there's a lot of value in trying to simulate different aspects of the brain in order to get insight about it. So I'm going to show you an additional neural network model that's also very popular and widely used, not nearly as much as the multi-layer perceptron, but pretty widely used. Furthermore, this has the interesting property of being an unsupervised learning algorithm. And so we'll get a feel for what that type of learning algorithm involves as well. In the end, as often happens with unsupervised learning algorithms, you kind of still need to do something with what it produces. And so we're actually going to use our unsupervised learner as a building block for building a full-blown classifier. But in doing so, we're going to get to have some experience of what kinds of outputs an unsupervised learner produces and ways that we can reason about those outputs. So what is this thing and what's its inspiration? This is called the Kohonen self-organizing map, and it is typically abbreviated as a SOM for self-organizing map. So I'm going to start by talking about its biological inspiration. Its biological inspiration is regions of the neocortex in the brain. So, anybody ever heard of the neocortex or have any familiarity with what it supposedly does? Okay. So, the neocortex is a region of the brain that tries to maintain abstract representations. So already we're talking about a neural network model that's not trying to model things so much on the level of an individual neuron as it's trying to be kind of a higher level, more abstract model that's thinking about things at a bigger scale than what we've been looking at previously. So what do I mean by an abstract representation? Well, let's just imagine a concept like a remote control, like we have here. So over the course of my lifetime, I have seen many remote controls, like a lot, in fact. And in that lifetime of experience with remote controls, my brain has built some kind of abstract representation of them that enables me that when I see something new, which I haven't seen before, enables me to think about, is that a remote control or is that not a remote control? Okay. So one way that you can think about this process of building a representation is to think about what does it mean to even build a representation. So let's imagine that in my lifetime, I have seen 5,000 remote controls. Just as kind of a starting point, right? Well, presumably for me to call these remote controls, these 5,000 have something in common with each other. You know, there's something about them that makes them remote controls, whereas other things are not remote controls, okay? But furthermore, even if I see the same remote control several times, I don't necessarily see it exactly the same way every time. You know, it might be farther away, it might be closer, what have you. It might have gotten a smudge of dirt on it. In my house, they might have gotten a lot of smudges of dirt on them. So we try to think about, well, what does it mean to say I've got an ideal representation of it? And one way of thinking about this, which is the solution we're going to see in the self-organizing map, is the following. We can calculate an ideal representation by averaging all the examples that we see. So let's imagine what this might mean in the realm of handwriting. You know, the problem we've been working on, and the problem we're going to continue to work on this week, right? So in the realm of handwriting, what we have are these binary pixelated images, right? And so a letter A consists of a bunch of pixels, kind of like this. And then there's this other letter A that maybe looks a little different. You know, maybe this one was at a kind of a different angle over there. And then maybe this little dash in the middle was kind of different. So we can think about what would it mean to find the average of the two, right? So conceptually speaking, you can imagine that the average of the two images is just the average, or for every pixel, the average of the values of the pixels. Now, by itself, that doesn't seem terribly helpful since we've been using binary images. But where there's a will, there's a way. And in particular, if there's a will to transform every true pixel to a 1.0 and every false pixel to a 0.0, in other words, turn our binary image to some floating point values, suddenly an average becomes really, really possible, right? And so if you think about these two and what an average would look like, well, we might imagine that where they have things in common, we'd have a really dark dot, you know, so that one is pretty dark there in the middle where the two crossbars intersect. But then elsewhere, we would have kind of lighter dots. So we got some lighter dots here and some lighter dots there. And then we've got some light dots going up this way and coming down that way. And then maybe some light dots coming up this way and coming down like that. And then where they intersect, you know, we get some darker dots. You know, that kind of a thing. Now with two images, this isn't necessarily deeply meaningful. It gets a lot more interesting if we have a lot more than two images. In other words, if we've got large numbers of images that are all getting averaged together, we can imagine some emergent thing which kind of like represents all of them at once. And we'll have really intense dark regions for the pixels that, in a sense, uniquely identify it as a category, and we'll tend to have lighter regions where it's not so strongly identified as a category. All of that said, I promised you unsupervised learning, and here I'm talking about categories, and so we get to this question of how do we even segregate them into categories? The answer is going to be the idea of a distance metric. So any unsupervised learning algorithm needs to have some bias or some way that it can say, these things are similar, these things are not similar. And so the most straightforward way to achieve this is to specify a function defined over the space of possible inputs that it seeks to classify. And that function gives a small value if they're similar and a big value if they're different. So any unsupervised learner is going to try to take really similar things and average them together and create different averages for things that aren't really similar to each other. So if we're going to do this, of course, we have to think about what kind of way do we know how many categories there are of things. And there are kind of two different philosophies that different unsupervised learning algorithms can take. One philosophy is basically to say there is a fixed number of categories. This has certain advantages and disadvantages. The advantage is it's kind of straightforward to understand what's going on. The disadvantage is that the number you pick might not reflect the number of categories that are actually out there, right? So then the alternative approach is what we might call density-based. In other words, try to get the same or similar number of examples grouped by a density cutoff. So but what do we mean by a density cutoff? So if we can think about, well, if things are within a certain distance of each other, that's going to emerge as a cluster, for instance. The data structure we're going to look at, the self-organizing map, is fundamentally more in this world, but has certain aspects of this world that influence it in addition. So again, fundamentally, we are going to have a fixed number of categories. But what's unique about the self-organizing map is that the categories are not hermetically sealed from each other. They actually kind of influence each other. They gradually fade in and out from each other to each other. So what's that mean? What's that going to look like? So let's imagine then what a self-organizing map is like. So in a self-organizing map, we have a grid. This is going to be especially fun because the contents of our grid is going to be more grids. That is drawings. So you'll just have to forgive me for that. We're going to make this, say, a 4x4 self-organizing map. So we look kind of like this. And so each of the cells in this map, each of the boxes in this map is a drawing. Okay. Now, it's not going to be a binary drawing. It's going to be a drawing rendered in floating point. It's going to be a continuous drawing. Why? Because it's not really a drawing by itself. Instead, it's going to be an average of many drawings that have all come across it. So in practice, what does this kind of thing look like? If we've trained it on a set of handwriting samples, we can envision that this map is going to have regions that are specialized in particular letters based not on a category that's been given beforehand, but instead on their similarity based on our distance metric. So an aspect of this that could be really interesting is if you've got a category like Y, where some of the Ys kind of look similar and other Ys look really different than those others, the self-organizing map can kind of grow regions that represent them individually that aren't necessarily even near each other. So what might something like this look like? Well, you can imagine in this extreme corner, you've got a very firm letter A. And let's imagine here you've got some slightly vaguer A's. And then in here, maybe you start having something that's kind of like half A and half H, where they've got a strong crossbar in common, but then things are a little sketchier when it comes to the things near the crossbar. And so you go down a little bit, and this one starts to become a bit more solid on the H, but there's still kind of a ghost of an A hanging out in there. And then maybe down here, you've got something that's a really emphatic letter H. And you can imagine this self-organizing map creating these different regions that have a certain amount of continuity in their transitions as you go from one to the other. And generally speaking, that's what a self-organizing map would look like. Now, as the user of this data structure, you have to make this important decision from the get-go, which is how many elements are you going to have in the map? So to some degree, you're really going to want to know ahead of time, like, if I've got a lot of data samples, I want to make a map that's big enough to contain them. But it's not just about the number of data samples, it's also about their overall heterogeneity. And the self-organizing map can actually be a really valuable tool to learn that about a data set, to get a feel for how much diversity is there in the data set. And that's a way that the self-organizing map is often used in practice, is it's not always used as a component of some system that you're going to deploy. It can be used just to try to gain a summary version of what a data set actually looks like. You know, if you've got 100,000 samples in your data set and you just want to get a feel for, if I could look at, say, a 10 by 10 self-organizing map where I get 100 averages of what these different things look like, you can get a really nice overall feel for what the different characteristics of the set are like. From there, you can imagine expanding the map. So you might go from a 10 by 10 to a 20 by 20, and then see, was there diversity in the set that got hidden or concealed when I looked at it with a smaller sum? Maybe with a bigger sum, I can see it at a better level of detail. And so you can use these as a really powerful technique for data exploration and the like. You have a question, Dan?
Well, I was just wondering, when you determine the number of categories, is there any guarantee that your self-organizing map is going to fully utilize them all? Or?
So that's a great question. And the way we're going to implement them, there will be something in every square. I will say confidently. There are ways to implement them that don't have that guarantee. And I'll explain what we're doing that does bring that about. Or mostly guaranteed to have something in every square. So the way we're doing them, once you've passed your whole data set through it, you'll almost certainly have something in every square. Cool. Any other questions so far before we do a somewhat deeper dive into how the data structure works? Yeah, Innocent.
Actually, so what is the intention of the data structure? You know how like a perceptron, we trained it and then give it data to give us what we think the data is.
Right.
Given a given symbol.
Right.
That we trained it with. In this case, if this is not supervised, like what does it do?
So in effect, it gives you this map, this visualization, and then when you give it a sample, it'll tell you where on the map it has the strongest response. So you can actually do fairly cool things, like you can have it respond with a heat map, where you have it say for areas where it's a really close match, you maybe color them bright red. For areas that are less of a match, you color them in a dimmer color, and so forth. Because there are no labels, it has just found categories, right? And so by themselves, they don't really mean anything, right? They don't, because it's not supervised, we haven't, as humans, imparted any semantics to those categories. They're just kind of there, right? Now, the categories are very real in the sense that they emerge bottom up from the data as things that have a lot in common. But ultimately, if we want to do something concrete with it, we actually have to build some kind of post processor onto the map for it to tell us something intelligible. So I think you can see that it's not all that difficult to build a classifier on top of this, right? You know, we can find a way, and I'll explain one technique for this. We can find a way to say, you know, this really is the letter H. And if the self-organizing map really likes an input at this cell, then we're going to go ahead and spit out that it's an H. You know, there are ways we can do that. What's cool about using a self-organized map for that is that the data structure itself is intelligible. That is, unlike the case with the multi-layer perceptron, with the self-organizing map, you can actually look at the map and see how it has organized its training data, which makes the results intelligible. Let's just say I personally have a strong preference for this approach. And I think it emerged in part because as I was learning about machine learning, I found I had a preference for algorithms where I could actually have a chance of debugging them, which is fairly difficult with a multi-layer perceptron. But with a self-organizing map, I can just pull up the map and I can see how it's actually organized my inputs. And so I'll be perfectly honest, I love this data structure. I've used it heavily. I've written papers about it. You know, it's not as popular as the multi-layer perceptron, so it goes. But for me, I have a definite fondness for the self-organizing map. Why? Because deep down, I think I'm just not smart enough to use a multi-layer perceptron well. I really like being able to look at what the data structure is telling me. And so, yeah, I've had a lot of fun with these things over time. Yeah, I have thrown these on robots, all kinds of stuff. Yeah, it's pretty cool. It's got some disadvantages, and we'll see what those are as well. But yeah, overall, this is a really cool data structure. So how does it work? So I'll first talk about how it works in terms of, imagine it's already been trained. How does it classify something? And then we'll talk a bit more about the training process itself. First, let's think about the classification process. It's actually brutally simple. You present some example to the map, say a drawing of a letter A, and then it will do a comparison between this and every single square in the map with the distance function. And the one that's closest is called the winner. And that's considered to be how it has classified it. So if I present it to the map and it decides, you know, 3,2 is the best match, that's what it's going to return as its category, as it's labeled. Yes?
Just out of curiosity,
Yeah.
say in the odd eventuality that there are two things in the map that it determines to be the winners.
Right.
How does it determine which one's better?
Some arbitrary tie break that you coded in.
Okay.
Like, it all kind of comes down to, does the winner have to be a greater than or equal to in your for loop? You know, that said, because of the way it self-organizes, in practice, if there's any ambiguity, they're probably kind of near each other in the map. So, you know, and there's a sense in which it might not even matter very much when those ambiguities arise. Now, this is, of course, just one way of using it. You could, you know, instead just have it produce a heat map or whatever. But this is a common way of employing it in practice simply because often, at some point, we're just done with the algorithm dithering and we need an answer. And so saying, okay, let's find the single best one is a really common technique. Yeah, David. Yep.
It won't actually say, like, this is A.
That's right. Yeah. Yeah.
So it essentially classifies almost just like K and M? It just learns in a different way?
This has astonishing commonalities with KNN, right? It uses a distance metric. A big difference with KNN is the idea of averaging. So here we're saying our budget is 16, right? We're using a 4x4 map. KNN has no budget, right? You keep throwing things into it and it just sort of keeps merrily trucking them along. This has more of a budget and says, okay, at some point we just start merging these things together in effect. So I'd say that's a distinction between this and KNN. That's very, very important. But KNN ideas wind up being pretty influential. One way, for instance, that you could build a classifier off of this is like do KNN backwards. So imagine you've trained the whole thing. Now for each cell, you want to decide what's my letter. Well, what you could do is take the averaged representation in the cell and perform KNN on your entire training set. And so you basically compare it to every input that came in with its label. And then whichever input, whichever top K inputs, you do the voting with KNN, and then you can just attach the label to the cell. And in fact, that's what we're going to do on this assignment. And so that's one technique for coming up with labels. What's nice about that technique is that every cell has a clearly defined label that we can easily understand from the training input. I've done other things in the past, like you can imagine taking each input, feeding it into the map, and then whatever cell comes up, you give it the label of that one. But the trouble with that is some cells might never come up. And so then if they come up in practice, you just sort of get unknown, throw my hands in the air as the label, which is astonishingly unproductive as a practical matter. Cool. Other questions so far before we start getting into the low-level details of the implementation? So one funny thing I'll mention is, this is named after its inventor, Tuovo Kohonen, who is from Finland, which, as we know, is an epicenter of a lot of computer science stuff. Linux was written originally in Finland, for example. His papers on the self-organizing map are the single most cited papers by a scientist from Finland. So, there's that. So this was developed in the mid-'80s, around the same time as the multi-layer perceptron, about 1984, a couple years ahead. Okay, so at an implementation level, so we've already talked about classify. So the idea of classify, right, is we have an input, and we're going to find distance to all of the cells. And like Dan mentioned, we have a KNN kind of thing going on where we find the distance to all of them, except here there's K is just 1, right? So then pick the first closest match. So this doesn't have the voting idea that we would associate with K nearest neighbor. So what about the training? Well, as you can imagine, training is actually going to be a little more complicated than classifying. But that's okay. So let's think about what the training process is going to look like. So we'll begin the start of time with a completely blank map. So all of the cells are just going to be all blank drawings. Just all zeros, okay? So given that, how does training proceed? Well, so we'll just put that in parentheses. Well, the first thing we're going to do is actually we're going to run classify of our input, and that'll give us a best matching cell. So the way that the training process is going to work in general is when we find a best matching cell, that cell is going to be changed the most. It's going to move the most in the direction of the input. But then importantly, its neighbors will also move in the direction of the input, but to a lesser degree. And that's what gives us the feel of continuity in the self-organizing map. So when it hits a particular spot, it affects not only that cell that it hit, but also the neighbors around it. So what does this altering, updating process look like? The way I like to think about it is to imagine it as a weighted average. Okay. So what do I mean by a weighted average? Typically, when we think about averaging two values, something like x plus, okay, I can't even write. Let me try that again. Something like x plus y over 2, you might notice this could be rewritten as 1/2 x plus 1/2 y. That's exactly the same thing. Once you write it that way, we can observe that there's nothing intrinsically holy about it being 1/2 and 1/2. Why, we could do 3/4 x plus 1/4 y. Right? What we do seem to want is the idea that these two coefficients, when added together, are 1. By doing that, what we're saying is that the result of our weighted average has a certain proportion amount of one contributor and a differently proportioned amount of another contributor. So this is perfectly balanced. Here I've got a bias towards x, right? But the point is I want those to add up to 1 in some way. So when we're thinking about updates to the self-organizing map, what we're doing is taking this idealized representation living at that cell, and we're going to perform a weighted average between that idealized representation and the input that just came in. So one of these is going to be our idealized representation. The other will be the input. And what we're going to do is find values to multiply them by so that we get the desired effect. What are some examples of desired effects? For cells that aren't the winning cell, we want the input's influence to be relatively small. After all, it wasn't the winner. Now, was it? So the closer you get to the winning cell, the stronger the input's influence should be. But now here's another consideration. We want to think about this emerging gradually over time, where each cell is like a weighted average, unbiased, of all the inputs it's ever seen. So what do I mean by this? So something that's actually really neat and interesting about the self-organizing map is that we can actually train it incrementally. So I could set up a self-organizing map on one of my robots, and as images come in, every time a new image comes in, I can update my self-organizing map just on the fly. Why? Because the training process is just find the winner, affect the neighborhood. So we can actually kind of update it incrementally on the fly. So what we want to do is construct how we do these incremental updates so that there's no particular bias between an input that I saw recently as opposed to an input I saw a long time ago. Here's a technique we can use to do that. Let's say I've got 3 numbers, okay? And just to keep it really simple, I'm going to make my 3 numbers 1, 3, and 5, okay? Now, if I average them as a batch, of course I get 3, right? 1 plus 3 is 4, 4 plus 5 is 9, 9 divided by 3 is 3. But what we need to think about here is actually doing this in an incremental way. So what do I mean by an incremental way? Well, I want it to be the case that when it sees the number 1, the average is 1. When it has seen 1 and 3, I want the average to be 2. And when it's seen 1, 3, and 5, I want the average to be 3. So a technique by which we can do that is to keep a count of how many values have come in. What do I mean by that? Well, with 1 is the only value. So I just put a 1 there. What about 1 comma 3? Well, at that point, I want to take 1/2 times 1 and 1/2 times 3, and that gets me 2. Now here's the next step. I could actually then take something like 2/3 times 2 plus 1/3 times 5, right? 5 having been my third input. And let's see where that gets us. 2/3 times 2 is 4/3, and then that's 5/3. That gets me 9/3, which is also known as 3. Now I want you all to see how I kind of made this jump or this transition here. All I'm really doing to produce this numerator is to count how frequently has this number come up, right? Or how frequently have I incorporated an average into this value? So what we have is, as a cell gets older and older, that is, as it gets trained more and more often, it gets a bias towards retaining more and more of itself and less of the input. But we try to have it incorporate enough of the input so that if you had permuted the order in which they arrived, you would still get the same stuff. Yes, David.
The reason why you're doing it by 3 is because when you added 5, now there's 3 things as well, even though you're still computing with the old average.
Exactly. Yes, Dan.
And each time you're only averaging 2 numbers. So like when you add a 4th number, you would take 3, because that was the average of the first 3 numbers, and average it with the 4th number.
Right, so we would say something like 3/4 times 3 plus 1/4 times 7, right? And so actually, if we calculate that out, we get 9/4 plus 7/4, which turns out to curiously be 4, which is the average of 1, 3, 5, and 7. Right. Now, actually, you can pay somewhat less attention to this value and a little more attention to this value. Why do I say that? Let's actually, I'll change over to red even. See, what I can do is I can just count how many times have I been updated. I find the reciprocal of that, and that's the value that I will multiply the input by. And then 1 minus that value is what I'll multiply the present input by. And that's how I get my incremental weighted average, just on the fly as I go. So that's pretty cool. In effect, what we have here is a slowly decreasing learning rate, right? Specifically, if we think about this as a graph, and we think of the increments on the graph as the number of updates after 1, after 2, after 3, after 4, and so forth, our learning rate is basically a hyperbola with an asymptote on the x-axis. So, in other words, the more that a particular cell learns, the more set in its ways it tends to get, right? It tends to be less open to change. There's an interesting analogy, biologically speaking, right, with how younger people tend to be more open perhaps to change or new experiences than older people. And this is a way of modeling that. Namely, well, an older person has seen a lot more stuff and is going to need a lot more persuasion to think things are different. This is kind of a machine learning way to think about that idea or that concept. But really, it comes down to the fact that once it's had a lot of experiences, there isn't as much incentive as to change or move to new experiences. So this is the basic technique for determining how we do the weighted average. There is, however, one additional component, which is how close is the node being updated to the best winning node, to the epicenter, so to speak, right? So we're computing this weighted average based first and foremost on our history. In other words, how frequently has this given cell been updated, right? So frequency of updates. Cells that haven't been updated frequently are going to tend to change more than cells that have been updated infrequently. But now there's another issue, which is distance. And here we need to be very careful to emphasize distance in the map. This can be really confusing with the self-organizing map. We're talking about two different distances. There are distances between these objects, and then there are distances within the map itself. Sadly, I can't think of another word than distances for both of them. To make it even more confusing, they're both going to be Euclidean distances. Yes?
With the distance within the map itself.
Yeah.
Is it the distance between the output of the map that it's kind of creating between its own output assets? And
Yeah.
the distance between the incoming input and the value you have in the map. It's another distance.
Yeah.
I don't know.
Okay. So
How would you explain the distance?
quick, I'll answer Dan's question, come back to that. Yeah.
So you're essentially just taking the categories and using them as inputs in your distance function. So like take two categories next to each other and I put them in the distance function and you're using the same distance function?
Not exactly, no. Yeah, so here's a way to think about it. Let's say that over here is our best matching node, okay? So when we think about how things are influenced, this best matching node changes the most. Now these nodes here, the ones in green, are all going to change the same amount, but less. And the degree to which they change will be based on the distance and the coordinates of the map. Yes, David.
Extend it to any other map, or just the one direct?
Oh, it'll extend.
Okay.
Yeah, yeah. Right. So then, let's go with blue. So then these guys, so note that in the same color, they're all the same map distance from the winning node. So these are all going to be scaled the same amount, but a lesser amount than the green ones and still lesser than the red. And then I'm going to have to make up a color now. Then, you know, this and this. Okay, it made up a color for me. Okay, that is not good. And then up here, of course, it goes off the map, which is fine. So we're just going to treat this as a flat two-dimensional plane. We're not going to say we've got neighbors across the boundaries or anything. And so forth. You know, so the further out you get, the less influence there is. So let's think about then, how do we quantify that influence? Yeah, Mitchell. In practice, it's easier to calculate for every cell, and at some point it'll start being 0 when you've gone too far. Yes, Dan.
So are we essentially just using the Manhattan distance between cells?
No, we'll use Euclidean distance. So like the distance from here to here is just 1, and the distance from here to here is going to be like square root of 2 or whatever.
Okay, if it was Manhattan, that would be the same as just going 2 straight over.
Exactly.
Okay.
I mean, there's no like intrinsic reason that you couldn't use Manhattan, but for the illusion of continuity to be produced in the map, it's kind of nicer to use this Euclidean distance. So how are we going to calculate this? Well, easiest way to do it is, we need to find the Euclidean distance in the map, but then we also need to scale it in some way, right? Because what we want is to get a result that's a 1 when the distance is 0, and then slightly less than 1 for the green ones, slightly less than that for the blue ones, and so forth. So here's how we might go about it. We can take our distance, I'll call it distance sub m because it's distance in the map, okay? And we can divide it by a value that we're going to call the radius. So the radius represents like how far out in the map we want the influence of the cell to be able to reach. And then this value, we ultimately will subtract from 1 with the idea that we won't let it go below 0. So if it starts going negative, we say it's too far away. So that's the basic idea. And so then that gives us an additional scaling factor which plays into this update. So if we set everything up correctly so that we have a 1 when we're on the winning node, we just use this value here, 1 over the number of updates, right there, as our learning rate. But the farther away we get, what we're going to do is also multiply this by this distance scaling factor that we just went over. So the further away we get, the less and less influence our input is going to have until it just diminishes to nothingness. And once it's 0, of course, at that point, the node's going to be left alone. So you can use different values for this. For this assignment, it works pretty well just to use the length of a side of the map, the width of the map. So if you've got 4 cells, you can give it effectively a radius of 4, which means that for far off diagonals, you'll have 0s, but in practice, it's going to be influencing most of the map. And that does a lot to produce some nice continuity. Having said all this, you may be wondering, well, what does this actually look like? Funny you asked. So here's a screenshot from my own solution for the letters A and H on a 6x6. So you see you've got a really strong A over here, and then H is really strong over here. And as you go towards the middle, they tend to fade into each other. Now, of course, the more letters you have, the more regions, the more territory will be divided among different regions as you go. But this gives you a feel for what the data structure is going to look like. And so the drawing editor program has a tab called visualization. And once you've got your self-organizing map working, you can click on that tab and you'll see this visualization appear. Yes?
Do we ever discuss what the map looks like when you have nothing in it? Like when you put an A to it, is everything A or is just one cell A?
What'll happen is like this will be heavily A, and then because what'll happen is, right, it's going to pick a corner based on whether you're using less than or equal to. So then from that corner, you'll have a really strong A, and then the A's fade out as you go away.
If it's like more different than the previous one you put in, that's how it
Yeah, yeah. And so then, yeah, if a really different A comes in, then it can strengthen different areas of the map and so forth. So obviously a disadvantage to a big map is that it greatly increases the running time of the algorithm, because the running time of the algorithm depends on how many cells you have in the map. So if you've got a really big map, this can run really slowly. Good news about it, though, is you only need to make one pass through the map with your inputs, thanks to this incremental averaging scheme that we're looking at. And that's pretty much the map for now. Yes?
Kind of following up on what Dave was saying.
Yeah.
When you do your first set of data that you're going to train, it compares everything to a completely blank map.
Yep.
And so it pretty much just arbitrarily picks the upper left-hand corner.
Yep, exactly.
And then the second piece of data that it has, it compares to an A and a bunch of slightly faded out A's.
Yes.
And then it finds which one of those things it's closest to. So it
Yep.
calculated the whole map the first time through.
Yeah.
Oh, okay.
And then the second time through, like say you've got two letters, well, that H is probably going to take over that lower right corner that's white or whatever.
Okay.
Then if another letter comes in, it'll pick, say, a fairly faded A. It'll train pretty strongly on that, and then it'll start taking that over. And just over time, you know, they stake out territory. Yeah.
It gets faded because it's compared with white, and that's how it's like literally fading away with the.
Exactly. Right, because of the distance, when we do the weighted average, there's only a small amount of it, and so it looks really faded. Yeah. Just as it goes. Yes?
So what if you train it to like NH and then ask it about O? Is it gonna choose between the two, the thing that looks more like O?
Yep. Right. If it's never been trained on O, and you ask it about O, it's gonna have a headache. In effect, right? It's gonna be confused. It's gonna find the drawing that's closest to an O that's already in the map.
And
Yeah.
is it gonna use the same value to also affect that thing that it thought was an O? In terms
If
of-
it's training it. So like, say you've got this map right here, and now you throw an O at it. It's gonna go through here, and it's probably gonna pick one of these middle ones that's kind of halfway between an A and an H. That's probably where it's gonna have the most intersecting points with the O. And it'll, you know, plant its flag there, and then start moving out from there and influencing its neighborhood.
You can make it dumb if you want, like by messing it up. Let's say.
Oh, as with any machine learning algorithm. Oh yeah. Oh yeah. Yeah. You know, so the O will start somewhere in there, and then it'll eventually, if you get a few more O's, it'll eventually strengthen that area, and so forth. So this is modeling the idea that in the human neocortex, thinking back to the remote control I talked about earlier, I don't only have one image of a remote control. I've got lots and lots of images of different remote controls, right? And those different images of the remote controls are ultimately organized in a cortical map, very much like this, where I've got different regions of the cortex that have specialized on remote controls, and then there will be sub-regions for remote controls, maybe of some different shapes or colors or what have you, and so forth. Self-organizing map isn't quite so sophisticated. You know, this is just one flat, one level thing. Connoisseurs of self-organizing maps have come up with hierarchical self-organizing maps and the like, to be sure. So there's a lot you can do with this. For this assignment, we're going to be focusing on the basic data structure. Cool. All right, let me begin going over with you the code that you're, oh, Mitchell, yeah. Yeah. Part of the beauty of this is you can represent it literally however you want, right? As long as you've got a way of defining a distance between objects, you can have a self-organizing map whose cells are literally anything. And as long as those objects can be represented in floating point in some way. So Why don't you make your example a little more concrete?
Well, just like, I've seen with machine learning algorithms where they'll like have a stick that you learn to walk or a car learn a certain path.
Right. We'll be looking at that kind of thing more in the next assignment when we look at reinforcement learning. But in these terms, well, here's the way you can think about it, right? So you mentioned the idea of a path to follow, right? So you give it multiple examples of different paths, which could then be averaged together in some way, where you have a visual representation of the path that lets you visualize the possibilities, but the underlying data structure could be just something like a linked list or something that's saying go here, go there, or whatever. So what it really comes down to is if you can define a distance and a way to calculate averages, you can use a self-organizing map. Yes?
Kind of following up on the path right there, with the cells and are the categories be a complete path? So we've been like comparing complete paths to each other, or?
Right. Yeah. Yeah. Given the example he was just speaking of. Yeah. Yeah. So yeah. So it would be but really anything. This was originally actually developed for sound recognition. So I do not want support assist during class. These were originally developed for understanding sound, and so the cells were actually linear time sequence sound waves that were coming in. And so this provided a way to visualize what do groups of related sounds look like. And I think you can see how you would readily find this applicable for a sound recognition problem, if you could see something similar about the sequences. All right, let's begin exploring the code. Now, the zip file for this is not a new IntelliJ project. It's files that I want you to add to your current project for the multi-layer perceptron. So I'll go over it here on the website, and then we're going to walk through the files themselves, and I'll show you the functions you're going to need to write. So these new files are mostly going to go in a handwritinglearners.som package. So you'll want to add that SOM package under handwriting.learners. And then I've got a file som6.java that goes straight in handwriting.learners. That's like, here's a deployable SOM that's a 6x6. So what are you going to be working on? There is self-org-map.java, which is the basic infrastructure self-organizing map. You're going to implement best for, which is going to be our classifier that finds the best point. Train,